Okay, I think we can get started. NPTEL colleagues, if you start the recording or something.
Hello,
Maybe.
namaskar. Namaskar.
Namaskar, sir. Maybe I'm just
I
trying to
think
see.
the recording part the studio people do, I think
They do
it's
it.
already there.
Okay.
Probably one of our coordinators who used to be there, probably they will join, I think.
No, Amrita can't join today, but
Okay,
it says already content is being sent to custom live streaming service. So fine. I
okay,
think we're all set. Thank you,
okay.
sir. So
Um,
let's get started. So this, well, firstly, thank you for joining on a on a Saturday, a holiday. And also for a couple of lectures that are pretty heavy and technical. And in fact, when I planned this, it was planned as just a single lecture, but it turned out to be longer than I had thought, and so I split it into two lecture recordings. Um, and of course, this is not really specifically true about ornithology in particular, but all the lectures that I've been dealing with, right from asking and answering questions in and approaches to science. Then the second part was the research design or study design. And finally, this pair of lectures, which is on data analysis and visualization. Of course, just an introduction, but even the introduction is quite long. So all of these are relevant to any aspect of science, particularly ecological sciences that I'm familiar with. Um, so in this pair of lectures, I covered quite a lot of ground from, what are some different types of data, with our categorical, ordinal, interval, ratio, circular, and so on. How you might summarize those data, how you might visualize individual sets of data. Then, of course, introducing the idea that when we are collecting data, what we want to do, we're collecting a sample from a population. And so the purpose is to say something about the population being a much larger set of entities than what we've been able to measure. So we have a sample estimate of what's called a population parameter. One common estimate is the mean, one of the measures of central tendency, but of course we discussed other measures of central tendency as well, including the median, which is more robust. That means it's less sensitive to outlying individual data points. Talked about the mean, so we talked about measures of central tendency, and then of course how we might look at variation, measures of variation, and starting with the range and the interquartile range, and introduce this idea about quantiles or quartiles are one a particular set of quantiles or percentiles, you can call them, which we may be familiar with from competitive exams. What percentile did you score into, and so on. And then, so one can use, for example, pairs of quantiles to illustrate variation in the data. For example, the range between the fifth fifth percentile, sorry, 5% percentile and the 95% percentile. And the range between those encompasses 90%, the central 90% of the data, and so on. You can choose any set of quantiles or percentiles to choose as your range. Of course, the min-max is the difference between the 0th and the 100th percentile, right? So the minimum is nothing lies below the minimum, and everything lies below the maximum. So 0th and 100th percentiles. But as we know, those are not robust, they're sensitive to outliers. We also looked at other measures of variation, for example, the classic standard deviation, um, and tried to go through that standard deviation. In fact, related to standard deviation, there's a question that was submitted through the Google form. Let me just pull it up. It's by Sakshita, who I guess is not here. But Sakshita asked the formula
I,
of... Sorry.
I am here.
Oh, you are there, sir. Okay,
Yeah.
great. Excellent. Um, and you say the formula of standard deviation is root. So basically, it's n minus 1 the denominator. Why does it decrease as more samples are added? And so I mentioned this in the lecture, Sakshita, but it requires a bit of thought. So I said that whenever we add one more sample, not only does the n increase by 1 in the denominator, but also the x minus x bar also increases by some quantity in the numerator, right? So x minus x bar is in the numerator. So the deviation of every data point from its mean, from the mean of the data. So if the mean is 5 and I add the value 3, my n increases by 1, but also the numerator increases by the value 3 minus 5, which is minus 2, which is squared, of course, becomes 4. So every additional data point increases not only the denominator, sorry, but also the numerator. So what I would suggest, Sakshita, just to satisfy yourself and never take, especially these quantitative arguments, never take my word or anybody's word for granted. It's useful to just try it out yourself. And you can do this in any spreadsheet software like Excel. And if you have just a set of data in a column, you can calculate in the next column a mean, and in the column next to that, the standard deviation of in a running way. So first with just the first row, the first data point, and there's no standard deviation if there's only one data point. As soon as there are two data points, you can calculate the standard deviation. And as you add data points, you can keep calculating the standard deviation. And you can see how the standard deviation might bounce around a little bit, but it won't systematically decrease. And that's because both the denominator as well as the numerator are increasing with every additional data point. Okay, so therefore, on average, just like the mean, because in the mean, by the way, also, if you notice, in the mean also, there's a n in the denominator. So why doesn't the mean keep decreasing? Well, it doesn't keep decreasing because when every additional data point, there's an additional number added in the summation in the numerator, correct? So it's the same kind of logic there. So the idea is that in our sample, we are sampling from a population. Let's say we're sampling length of peacock tails, no? That's one of the examples given. And the length of peacock tails in all of Delhi state. And there may be, I don't know how many peacocks there are in Delhi state, maybe a few thousand peacocks. And we start with 1, 2, 3, 4, we keep measuring more and more. Now, the idea is that there is some true population mean tail length in Delhi state of peacocks. Some true tail length, which is the mean. If we were able to measure the tail lengths of all the peafowls, all the peacocks in Delhi state, there'll be some true mean of that. Let's say there are 2,350. And we are able to catch and measure all of those. Then there's a mean. That is the population mean. Now, of course, we can't capture and measure all these. So that is an unknown to us. But as we keep capturing and measuring, we hope that the mean that we get, the sample mean, somewhat approximates the population mean. So there's a true population mean, and then there's the sample mean that we have. And similarly, there's a true population standard deviation. So among the 2,350 peacocks and their tail lengths, there is some variation. And if we take the standard deviation to be a measure of that variation, there is some true values. There is some population value of that standard deviation. Again, we don't know what that population value is, but as we collect more and more samples and calculate the sample standard deviation, we hope, if there's no bias, etc., then we will approximate the population standard deviation with our sample standard deviation. Of course, the sample mean and sample standard deviation are more likely to be close to the population mean and population standard deviation if our sample size is large, because then there's less likelihood that just we happen to catch more long tail males than there are in the population, or more short tail males. Because if by chance we can do that, just like when you spin a coin, by chance we can get a series of heads rather than exactly 50-50 heads and tails. But as you know, by spinning a coin, if we spin lots and lots of coins many times, then we'll most likely come to somewhere near 50-50. But we can't get something very extreme. You can't get 100 heads or 90 heads and 10 tails. That would be very, very unlikely. So anyway, so we more likely to approximate the population mean and standard deviation from our sample mean and standard deviation if the sample size is large. And of course, if there is no systematic bias, either bias in sampling, that is, we let's say longer tail males are easier to catch, suppose, because they move more clumsily and in whatever catching device we have, they come more easily. So if we have a bias towards catching long tail males, then no matter how much sample size we have, our sample mean is going to be biased towards a higher number, longer tail, than the actual population mean. So if we are biased, then we are stuck. We are done for. There's nothing we can do. So we have to be very careful not to be biased. So either we have a sampling bias like that, or there may be a measurement bias. That is that the tool with which we measure the actual tail, we might have a representative sample in our hand, but the tool with which we measure whatever that is, vernier calipers, measuring tape, whatever it is, if that is biased, that is if it's calibrated wrongly or whatever else, or we just use a faulty measurement method, then that could be biased. So assuming no sampling bias and no measuring bias and a large enough sample size, then we can assume that as our sample size gets larger, we would be approximating the population mean for the peacock tail length. Now, so just to come back to that question, Sakshita, I don't know if you're satisfied with the answer about why the standard deviation doesn't keep decreasing as we increase our sample size.
I am. It makes sense now.
Yeah? But do try it out in an Excel.
Yes, I'll do that.
Yeah.
And because the standard error has again a root of n in the denominator, that's why it is going to.
Yeah, because nothing is increasing in the numerator for the standard error.
Hmm.
The numerator stays the same.
Right.
And the denominator is increasing. So that's why the standard error decreases. So,
Yeah.
so that brings me nicely then to the next part, which is that, okay, fine, we've gone out and collected some data and of peacock tails. And we, our goal is to try and get as close as possible to the population mean tail length in Delhi state. But how do we know whether we are near that goal or not? And that's where we bring in the concept of precision. That is that if I collect a sample of 100 peacock tails, tail lengths out of the 2,350, then that's just one sample. By chance, I got these 100. If I had gone out a different day or a different part of Delhi or whatever else, I would have caught another sample of 100 with a different set of tail lengths. So my sample of tail lengths is just one particular sample out of many, maybe infinite possible samples of 100 peacock tails. And if I had had a different sample, I would have got a different mean. Now today I have this 100 in my hand, and I've got 100 data points. From that I calculate a mean, and I think this mean tail length is the be all and end all. But if I had done it tomorrow, or if I had gone slightly differently, or chosen a different set of random numbers to choose, then the mean would have been different. And so that's a second kind of sample. If I had done it a third time, 100 peacocks, my mean again would have been different. A fourth time would have been different. So every time I go out and sample 100 peacocks, the mean would be different. And the crucial thing to understand is that if every time I go and sample 100 peacocks, if the means are very different from one another, then that means there's a lot of variation in the population in peacock lengths. Because imagine if all peacocks had exactly the same tail length, I calculate the mean of this 100 versus the mean of that 100, the means would be identical or very close to each other, correct? So if there's very little variation in the population, the underlying population, then whether it's this sample of 100 or that sample of 100, I'll still get very similar tail lengths. But if there's lots of variation in tail lengths in the population, then every time I go out and sample peacocks, I get a different mean. The other reason I can get a different mean is if my sample size is very small. So if I only calculate a mean of tail lengths of 3 peacocks at a time, then I'll measure these 3 peacocks, get a mean, measure those three peacocks, get a mean, another 3 peacocks. I'll get very, very different means because the variation is very large. So, and that will be less variable, the means will be less variable if my sample size increases. So the precision then is a measure of how close my particular sample of peacock, the mean of my particular sample is, to other possible samples I could have got if I had sampled tomorrow or differently or whatever else. And the precision is estimated. Usually we do this as by calling by measuring something called or calculating something called a confidence interval, which I mentioned. So we have a confidence interval. So I say that my mean peacock tail length is 140 centimeters, and the confidence interval is between 135 and 145. That's an example of a very tight confidence interval, 135 to 45. That means for now, let's just say that our best guess is the true population mean lies between 135 and 145 centimeters. So that's a very tight confidence interval. But if I have a small sample size, or if the underlying variability in peacock tail length is very large, then maybe the mean I get, the confidence interval I get is between 100 and 180 centimeters. That's an 80 centimeter span between the lowest number and the highest number possible. That's a very, very loose confidence interval. So our goal really in measuring peacock tails or whatever that we measure is to try and get that confidence interval to be tight. We have no control on the actual mean tail length, right? We don't even have an opinion on that, right? We just want to know what it is. So your tail length, you might get a small number or large number. That doesn't determine whether you're successful. What determines whether you're successful is how precisely you're able to measure that tail length. And so therefore, we have to understand the concept of precision quite carefully. And unfortunately, I think that most practitioners, young scientists, ornithologists, and others don't really understand precision very well. Because it takes time to wrap your head around the fact that the particular sample you've taken of whatever it is, number of peacock tails, is not the be all and end all. It's just one possible sample that you could have got. And there are many, many other samples you could have got, which would have given you different means. So there's nothing greatly special about the particular sample of 3 or 30 or 100 peacocks that you measure. And that's something hard for people to let go. They think that what I've measured is the be all and end all, but it isn't. It's just one instance of the outcome of sampling from the population. So in the lecture, I talk about how in principle we can imagine, and then we do it by simulation on a computer. We can imagine from a population, let's say 2,350 peacocks, we take samples of, let's say, 30 peacocks, calculate the mean, take another sample of 30 peacocks, calculate the mean, and another sample of 30, and do that many, many times. And then look at the distribution of the means. And that distribution of means also has some properties. It has an overall mean, so the mean of means of the different sample means. So each mean is called a sample mean, and then there's the mean of the sample mean, so overall mean. And that distribution also has a standard deviation, which in the terms of precision, we call the standard deviation of sample means is called the standard error. So the standard deviation by itself is just you apply a formula to a set of numbers. If those set of numbers are the raw data, then the standard deviation that you calculate is a measurement of how much the data vary. If the numbers on which you calculate the standard deviation is the sample means, right, then that standard deviation is telling you how the sample means differ from one another, which is called the standard error. So I repeat that a couple of times in the lecture. It's worth again going over that, looking at the transcript. Yeah, in both cases, we're calculating a standard deviation, but in one case is a measure of the variation in the data. In another case, it's a variation in the distribution of sample means, which is a measure of precision. So I talk about that using a Bootstrap. So in fact, unfortunately, in this particular online mode, it's not possible to get into some of the computational parts, which when I teach this in person, we use the software R and we simulate some data, and then we draw these samples again and again. And in that case, we know if we simulate a set of, let's say, 2,350 peacocks, we know the true value in that simulated data. And then we can take a sample of, let's say, 30, and then another sample of 30, and we can look at how those samples perform in relation to the true mean. In the real world, of course, we don't know the true mean, but in the computer environment, in the simulation, we know the true mean. And that's a very powerful way both to understand intuitively what we're doing in order to get as close as possible to the true mean. And of course, how you might actually perform some of these calculations. So for both of those, the simulation is quite useful. But in any case, in our particular context, online courses have their limitations. Apologies. We just have to understand it conceptually or try as best we can. And then, of course, we figure out how we can calculate the confidence interval from this distribution of sample means. If you want a 95% confidence interval, then you look at the 2.5th percentile and the 97.5th percentile. In between the two of those bounds lies the central 95% of the sampling means. And so we can use a percentile approach if we do a bootstrap, which is a computer simulation way of getting at this. Or if we can assume that the central limit theorem applies, and this lecture is full of new jargon, I apologize. The central limit theorem says that when you take samples from a population, and for each of the samples you calculate a mean, and then you look at the distribution of means, that most often resembles a normal distribution, especially when the underlying distribution is not too skewed, and if your sample size is large. And I'm not going to repeat again because that's there. Some amount of time is spent in the lecture on the central limit theorem. But the point is that if we can assume that our mean, the sample mean that we have got, is one instance that comes from a distribution of possible sampling means, and that distribution is normally distributed, then we can use some of the properties of the normal distribution to calculate directly the confidence interval without doing any computer simulation. And there's various things we talk about in the lecture about properties of the normal distribution, how you can think of the normal distribution as, if you subtract the mean from every data point and divide by the standard deviation, you come up with a standard normal distribution with mean of 0 and standard deviation of 1. And the standard normal distribution has some particular properties. And in particular, the property of the normal distribution is that if I take the mean of plus or minus 0.65 standard deviations, then that gives me the values between which 50% of the distribution lies, or the mean plus or minus 1.96 times the standard deviation, that gives me the values between which 95% of the population lies. So similarly, using that same kind of logic, if I am able to calculate the standard error, which is the standard distribution of standard deviation of sample means, then I can use those properties to directly calculate the confidence interval of my confidence interval around my best estimate. And if we can assume the normal distribution applies, then we can use that formula standard, which I think we alluded to just now, that standard error is the standard deviation divided by the square root of n. And we use that standard error now. In place of our standard deviation of the data, we use the standard deviation of the sample means, which is the standard error. And then we can take our mean plus or minus 1.96 times standard error. So minus will give you some value lower than the mean, plus will give you some value higher than the mean. And that is your 95% confidence interval. So you can say that here's my sample mean, and here's the confidence interval. And then you can look at whether that confidence interval is broad or narrow. It's a very broad confidence interval. Then you haven't trapped the population mean in a narrow enough interval. The population mean can be anywhere between the lower and the higher number. But if the confidence interval is narrow, then we have done our job. We've kind of trapped it. This is just a metaphor. We've trapped the population mean in a narrow band. And so we've really learned a lot about where the true population mean tail length might be. Yes, is that Sakshita again?
Yeah.
Yeah.
So I had a question about this. Can you give an example of when we would use something like 50% of the distribution lies in this confidence interval? Like 95% and 90%.
Yeah.
Could we say some 50%?
Sorry, you're breaking up a little bit, Sakshita, but I think I understand. So, so the convention, in the lecture, I've used examples of 50%, 90%, 95%, just to illustrate how we can define any what's called coverage, right? So 50% coverage, if we want the confidence interval, 50% confidence interval, we can calculate what those bounds are. If you wanted 90%, we can calculate. What 95%, we can calculate. So that was just to illustrate, and get you all a little more comfortable with the idea of this quantiles, quantiles being the values that divide the data into different fractions, different proportions. But in practice, in ecology at least, and maybe physics is a bit different, but in ecology, we usually use the 95% confidence intervals. It's just a convention that has developed over, I don't know, 60, 80 years now to use the 95% confidence intervals. So it's very rare that you see in published research in a peer-reviewed paper where people are using anything other than 95% confidence intervals. So remember again, the interpretation of the confidence interval is roughly this, that if I have, let's say, my 95% confidence interval for peacock tail length is 135 centimeters to 145 centimeters, okay? Then the very rough interpretation is that there's a 95% chance that the true population mean tail length, there's a 95% chance that it lies within this interval. And so therefore, of course, there's a 5% chance it lies outside the interval, right? You can never get a 100% confidence interval because that, according to the properties of the normal distribution, that goes from negative infinity to positive infinity. Even though, of course, tail lengths can't go below 0. But in any case, so 95% is what people use. Or if I had taken the 50% confidence interval, so in this case, if it's 135 to 145 or 95%, then 50% will be a narrower interval. Let's say 138 to 142. And then I'd say there's a 50% chance that the true population mean lies in this interval, 138 to 142, and a 50% chance it lies outside. So while in principle, you can choose any coverage that you want, 50%, 95%, and so on. And by the way, there's some statisticians who argue that 50% is an easier number to interpret because we have an better intuitive understanding. Okay, there's a half chance that the true mean is inside the interval versus outside the interval. It's a 50-50 chance. Whereas 95% versus 5%, these statisticians say is a much less, we don't understand it fully. And we make the mistake of assuming, even though we calculate 95%, we just assume that, yes, this is the lower bound, this is the upper bound. So we interpret it as though it's a 100% confidence interval, which it isn't. Now, although those arguments have been made, in practice, just to caution you, you would have to argue quite a bit with reviewers and editors of journals if you wanted to publish anything other than a 95% confidence interval, in my experience. Now, in the physical sciences, in physics and so on, very often when they calculate, because they are able to, if they're measuring some physical constant, for example, they are able to measure with much more precision, because also they have much less variability in their systems. Biological systems are characterized by variability, so it's very hard to trap the population mean in a very narrow interval. But in many physical systems, that is not the case. So sometimes they'll choose they'll choose confidence intervals which are 99.99% confidence intervals. And even those will be extremely narrow ranges because depending on what you're measuring, the physical systems are much simpler and much less variable. And the only thing that varies there is experimental error, experimental variation. Whereas in our case, peacocks as biological entities have vastly differing tail lengths. So I've forgotten now. Yes. So yes. So the question was, what about 50%? Sure, you can calculate 50%. Please remember what the interpretation is, how it's different from 95%. But scientists, like others, are creatures of habit. And when you're submitting your paper for peer review and so on, it's hard to get anything other than 95% decision past these people. If you are interested, actually, I can put on the Q&A, I can put a link to a paper or a blog post by one of my favorite statisticians, where he argues for why we should be using 50% confidence intervals. But in practice, it's not of great use to us mostly. Apart from just reminding us, it's an arbitrary decision, one or the other. Yeah, okay. So that's, I hope that's, it's a lot, but I hope that's relatively clear about the confidence intervals. I think in the lectures, then I moved on to not just measuring the, okay, good, I'll send it to you. Not just measuring a single quantity, like what is the tail length of peafowl. This is a silly example, no? Of Delhi peacocks. But a comparison. So you might want to measure, the difference in the mean tail length between Delhi peacocks and Haryana peacocks. And I don't know why you might want to do that. There may be other comparisons that are more sensible to you, but let's just go with this silly comparison. But presumably you have some real reason to to want to know if there's any difference and what's the difference between tail length of Delhi and Haryana peacocks. So there, the point is that there are two different populations in Delhi and Haryana. And now the question is, what is the difference and what is the precision of the difference? How confident can we be about our estimate of the difference? Now, Delhi and Haryana peacocks are examples of what are called unpaired data. So you can measure 30 peafowl in Delhi and you can measure 100 peacocks in Haryana. And each peacock in Delhi and each peacock in Haryana are unrelated to each other. There's no connection between the two. But whenever we make comparisons, they can also be paired data. For example, in the case of peacock tail lengths, we can ask, if we let's say measure the same peacocks in multiple years. So peacocks, as you know, they grow their tails long and then they shed the feathers in the non-breeding season and they grow them again in the breeding season. And we might want to know the first year when 1-year-old peacocks, I don't know if at the age of 1 they do grow the long tail, but let's say they do. 1-year-old peacocks, they grow their tail, and then we have the same measurements for 2-year-old peacocks on the same birds. And we want to know, let's say, if they have longer tails when they're 1 year older. In that case, we are measuring the same peacock, the same individual in year 1 and in year 2, correct? So the measurements are connected. Every peacock is measured year 1 and year 2. So we have what are called paired data. And you can't have different sample size. It has to be the same sample size in year 1 and year 2, because after all, you're measuring the same peacock. So if you measure 40 peacocks in year 1, it's the same 40 peacocks you measure in year 2. So that's called paired data. We can line them up in a pairwise fashion. And it's quite simple to analyze pairwise data, because all we need to do is take the difference between year 1 and year 2, create a new column in Excel or whatever, and look at all the differences, and they take the mean of the differences. And the mean of the differences, so if we have 40 peacocks measured in year 1, year 2, there'll be 40 differences, and the mean of those differences will be our best estimate of how different the tail length is in year 1 and year 2. And we can calculate confidence interval exactly the same way as we did before, because we are just a single row of numbers, except that that row of numbers is the difference between year 1 and year 2. So I've explained this in the lecture. So paired data are very simple. Unpaired data are a little more complicated, because we can have different sample sizes. We can't line them up and take differences one by one, pair by pair, because there are no pairs. So we need to calculate the mean of Delhi peacock separately and the mean of Haryana peacock separately. And then we take the difference between the means. And that difference between means, of course, is our sample estimate of the true difference in the population means. And then to understand the confidence interval, it's a little different, because there's a different standard deviation. There isn't just a single standard deviation. There's a separate standard deviation for Haryana peacocks and a separate one for Delhi peacocks. And then we have to calculate the pooled, that is the combined standard error from these two standard deviations. But there's a way to do it, luckily, and there's a simple formula that is there in the lecture. And once we have the standard error, then we can do the usual thing. So we have the difference between the means of Delhi and Haryana. We have the pooled standard error. We take 1.96 times that standard error to give us a 95% confidence interval. And then we can estimate what is the difference between what's the precision in the difference that we've measured between Delhi and Haryana. So that's one further kind of sophisticated. So we started with a single row of data. That's a single set of peacocks that we measure, and we just want to know what is the mean tail length. Now we've complicated a little more. We want a comparison of tail lengths, either year 1, year 2, or Delhi, Haryana, and we've done that. We figured out how to do that and to understand the precision in the estimate. Again, the idea is to have as high precision as possible, which is to have as narrow a confidence interval as possible, because that's the measure of our success. The actual difference that we find, we are not in control over. What we are in control of is the precision, as always. And then I'll not go over some of the other things we talked there in the lecture. There's odds ratio to understand whether the difference is, how confident can we be that the difference is on the positive side or the negative side. And there's a description about calculating the degree of evidence for the difference to be positive versus negative. And then the ratio between that is called the odds ratio. But let's not go over all that. It's difficult to do so without the slides also. But the last part is kind of important, because a lot of what we do in ecology is looking for the association between two variables. That is, if I have an X and a Y axis, I can draw a scatter plot, and I ask whether there is some kind of association, positive or negative, between the Y and the X variable. So the Y axis being the vertical axis, the X variable being on the horizontal axis. And so there are various ways in which you can try and understand whether there's an association. For example, we can ask, in the case of peacock, since we're on it, are older males tend to have longer tails? Seems like an interesting question. It's not some arbitrary thing I just made up. And so we would have age on the x-axis and tail length on the y-axis. And I guess we would have caught a bunch of peacocks. Somehow we knew their age and measured their tails. And maybe we expect naively, we don't know, but we expect that perhaps older males might have longer tails because they are more able to get resources, more able to fatten up before the breeding season, garner food, fight off other rivals, and therefore get more nutrition and therefore longer tails. So that's some reasoning we have, which is useful to spell out. So we want to know whether tail length and age are associated. And in the lecture, I first start with this idea about covariance, how we might measure covariance, and then correlation between y and x. And there's something called a correlation coefficient, which varies between -1 and +1. So -1 being they are perfectly negatively correlated, +1 perfectly positively correlated, 0 is no correlation at all, no relationship between the two variables at all. But what the correlation is very interesting and important, but what it doesn't do, it doesn't say, tell us how, by what magnitude the tail length changes as age increases. And for that, we need to break out our maths, our school maths, and think of the equation of a line, which in the lecture I call y is equal to a plus bx, a being the intercept. So what is the tail length? So this is mathematically, what is the tail length when age is 0? Of course, there is no such thing. And in fact, in many ecological situations, the intercept is a bit of a fictitious thing. It's a mathematical necessity, but it has no biological interpretation. So for example, in this case, there is no male with age 0, but it's just an extrapolation to the left to see where the y-axis is cut when x is 0. But more interesting for our purposes is the slope. So in y is equal to a plus bx, b is the slope. And the slope, the interpretation is for every 1 year, if age is measured in years, then for every year of additional age, by what degree does the tail length change? Suppose we are measuring tail in centimeters, so by how many centimeters is the tail length change? And if there's a positive relationship, then by how many centimeters does tail length increase with age? So that now is the domain to understand that equation and therefore get the slope, which is the main variable of interest, the main parameter of interest. We use something called regression analysis, and again described in the lecture. So there are many straight lines we could potentially draw through a set of data, or x and y data. And regression is one particular way of drawing what we might call the best fit line. And the regression line is the line that minimizes the sum of squared deviations to the actual data from the line. So all this is there in the lecture. I'm not going to draw it out or show it again, but there is a particular method to find the best fit line. Once you found the best fit line, that best fit line, any straight line in Cartesian space, that is with 2 dimensions, x and y, has an equation with the intercept and slope. So we can find out the intercept and slope, in particular the slope. And let's say we care about the slope. Is the slope positive, which means that tail length increases with age? Is it negative, which means that tail length decreases with age? Or is it near 0, which means it doesn't change? So the question really is, what is that number? Not just whether it's positive or negative, but what is that number? So if, for example, our estimated slope is +5, +5, that means that on average, tail length increases by 5 centimeters with each year of age. Yeah, does that make sense? So that is our estimate. That is what we care about. We want to know what is that number. And this is our sample estimate. 5 + 5 is our sample estimate. There is a true population value of slope, which unfortunately, as we've talked about many times, we don't have access to. We can't measure the true population slope, but we have our sample slope. And whenever we have a sample estimate, we need to figure out precision. And in regression as well, there is a way to calculate the standard error. And if you know the standard error, then you can calculate the confidence interval around the slope. And so now we have a way to understand not just the slope itself, but what the confidence interval is. And therefore, within what bounds have we captured captured, we could say, the population slope. And again, our confidence interval depends on the sample size we have plus the variation in the population. So if you have a nice big cloud of data, then there's lots of variation. And so we need a large sample size to get to a high precision. But if there's the actual population relationship between X and Y is quite tight, there's not much variation away in the Y direction, and I've showed a bunch of cloud points there in the lecture, then we don't need as big a sample size for the same amount of precision. So that's where the lecture leaves off. We're just scratching the surface of regression analysis, which is a very, as I say, very, very widespread and very popular technique to understand the relationship between Y and X, between two variables. We only scratch the surface because we've only looked at one predictor. So sometimes X is called the predictor and Y is called the outcome. And there are regression models where we might have multiple predictors, not just one. So, for example, in the peacock example, we might imagine that we think that it's not only age that affects the tail length, but let's say whether they live in more natural or more urbanized habitats, right? Because we imagine that has something to do with their nutritional status. So we might have habitat type as also something that we think affects tail length. There may also be something to do with the disease, let's say. Males that have been in fights or have had disease, maybe they have a different, we may imagine multiple different predictors of tail length. And regression analysis allows us to actually look at the effects of those multiple predictors at the same time. So don't only have to look at a single X and how it predicts Y. We can look at multiple X variables. And that's called multiple regression, which is one example of a larger set of analysis called linear models, but we don't have to go into that. But if and when you do research, you'll see very rapidly that if we want to understand some particular thing, like tail length, there are going to be many possible aspects of a peacock's life or habitat that might affect it. And so we're not going to do single regression, many single regressions. We're actually going to do multiple regressions. But we didn't get into that in this lecture. And I say it's just at the start. So can you believe it? At the end of, I don't know how many, 2 hours of lecture or something, we're only just at the start of looking at data analysis and visualization. But what to do? That's where we are. That was a very long recap. But I'll stop there. I know Sakshita said she would like to see that paper or blog post, so I'll send it out on the Q&A. And yeah, and if there's any other thought or question, right now on these two lectures? Please feel free to unmute since we are so few people.
That was a good recap. It was complete.
Oh, thank you, sir. Thank you.
It's nice. Initial lectures are also very diligently made. They are there in place. You have gone and kept explaining every detail neatly. I appreciate. I could get the feel, as you have mentioned, that it requires one or two more rounds of hearing too. Of course, I went slow. One round I have completed. Uh, every time passing and going back and forth, back and forth. And maybe one more round before the assignment is required, and then another round. That concept of R programming, you had indicated, that is new to me. I will just look into that and try to get a feel of that at some stage.
Yeah,
that's it.
Maybe I can, when I send out the link also that Sakshita wanted, I'll also put a link to some an introduction to R. So R is the software that most of us use to do statistical analysis and graphing, visualization. R is a programming language, which means that it's very flexible. So we can also do things like simulations and so on. And so most professional ecology researchers use R. But of course, it can be daunting if you're not used to programming. But anyway, it's quite simple. I did want to say that, the lectures that I've done, so this is the last series, but on asking and answering questions in ecology and research design, and then now data visualization and analysis. These are lectures that span an entire semester of coursework that I teach at a master's MSc level. So entire semester means I think it's something like 30 hours of class time. So 30 hours of class time have been compressed into a few hours over here. Without, and I fully understand, this is anyway, this is NPTEL online. It has its limitations.
Yes.
If you have a chance to do in-person courses, those are always better.
Yes. Your last few minutes at the end of the lecture, where you were telling how it is essential to get to know about this, get a feel of that, than getting it superficially. Very, very well said, and it is many times, as long as bits and pieces are understood, people start going forward. But if researchers have to do it, means they have to get it into the system. That's where your words were there of great importance. That last 2-3 sentences, I appreciate. It's very, very well said.
Yeah, thank you. I feel strongly about it because I know I was like this earlier. My training as a student was highly inadequate, and we used to view statistical analysis as a like a recipe book. You just follow the recipe, you do the calculations, and you get the result. But actually, the theory underlying that is important to know because we need to know what assumptions are being made. What are we trying to do in the first place? Most people don't fully understand it. So I see that while mentoring younger students also. But of course, I know in our course we have a mixture of enthusiasts who just want to know more about birds, and some who are on the research track, either as students or as faculty. For the former, all this can be ignored. If you want, of course, in the exam, you need to know some to pass the exam. But for those who are in the research track, I think it's really important to grapple with these issues and spend much more time, of course, than we have done so far. But yeah, I don't know about here, among the mix of people here, if anybody here is in a academic track, if you want to just put a thumbs up so that I know. Academic track work. Yeah, Neelam, okay.
Well, sir, thank you very much.
Yes,
It's
Mr.
a really complicated subject now, and thanks to you, but I will share my experience. Like the standard deviation, the standard error, all these things, when we were doing a sort of wage calculation across the industry, we used to hire the data scientist and compile all the things. So we had a tough time explaining to a common layman what is SD, what is SC, and why the wages are skewered. So as I was going through your lecture, so I was not relating with the trains of the peacock and other thing. I was correlating with the the data which I was struggling for years with no clear explanation. So it has really helped. So to say that only for the academics, this is applicable for day-to-day life, and it helped me to communicate with my son who is doing research. So it was just throwing all the things. He said, "Papa, you will not understand." So so it helps me to at least correlate what, like for the example, the R. So this is basically like used for the data crunching and simulation. So now I can always put 2 plus 2 together and to see like how useful this data visualization is. Thank you very much for enlightening us.
Thank you. I'm glad it helped in some way, even if not in the academic part, even other things. Yes. And of course, I also feel that as humans, we are curious, and we should be curious all through our lives. And especially sometimes I also feel that if there are concepts that I learned in school but did not fully understand, and suddenly I come across some YouTube video that explains the concept so beautifully, it has no relevance to my professional or personal life, but it's just so satisfying to be able to understand something. And I think that that's just a human characteristic, and we should keep being curious, keep learning. So thank you for your words. It's much appreciated.
Thank you, sir. Thank you.
Good. All right. We are at the end of our hour then. We can bring it to a close. And I just now in the next few minutes, I'll post on the Q&A with some of the information that I had mentioned. Yeah. So thank you all for joining. Take care. Have a lovely weekend.
Thank you.
Bye.
Yeah. Bye. Bye.
Bye.
Yeah.